Good morning, everybody. I was asked to give a very small introduction to the emergence of plate tectonics. That's a very difficult topic, and I'm going to give you a perspective from the back seat because, of course, I arrived later than the revolution, and I didn't play a very active role in it. But I think it's interesting to place it in a larger context. And here are years, and I think when we think about physical models of the Earth, it started quite early. By physical models, I mean physical models that were based on some physics and some calculations. I think it's important to note, for example, that Charles Fourier developed his theory about heat transport specifically to study the Earth's temperatures. And he, in fact, wrote that this was of the most important and most difficult problem. And I think most of the 19th century was devoted by models of the Earth because physicists and geologists were, of course, concerned about the Earth, but the physical theories were already made on a global scale. At that time, until early in the 20th century, mountain building was essentially attributed to shrinking due to secular cooling. And secular cooling was also used to determine the age of the Earth. You all know about the Kelvin problem and controversy. But it's interesting that, of course, people thought that it was interesting to look at the Earth in a time-dependent framework with the Earth cooling down, such that what we observe today is probably the result of years and years of secular cooling. People were already interested in rheology, and isostasy came, of course, quite early. But in terms of dynamics, there was little. There was almost everywhere there was arguments about whether the Earth was moving or not. It was clear that it was moving, if only because it was building mountain belts. But of course, things became gradually more and more specific. But we didn't know much about the Earth structure until the early 90s. The Moho was discovered in 1909. I would like to point out that before that, Robert Strutt, the fourth Lord Rayleigh, had argued that the continental crust could not be thicker than about 60 kilometers on the basis of heat flow measurements. Because I'm interested in heat flow, I thought it was worth pointing that this was made before the Moho discovered by seismologists. And of course, we by the 1940 or whatever, we had a pretty good idea of what the Earth's internal structure was. It was the seafloor mapping that got us into plate tectonics, really, and that was mostly developed in the after World War II. And I think one of the key issues that was grasped quite later and that didn't play a large role for the revolution in plate tectonics was the fact that most of the seafloor was basaltic in composition, and in those days, our understanding of basalts was not very good. Most petrology data, in fact, was the so-called granite problem, and it was realized quite late that basalts were probably the most important form of lavas on the planet, and the phase diagrams for basalts and for the melting of peridotite started to arrive quite late in history. You can rewrite history, but I think if this had been done a bit earlier, maybe we would have gotten to plate tectonics earlier, because of course generating basalts on the scale that we know is happening is a major problem. Just to give you another perspective, what happened with our understanding of the universe, the atom structure was basically sorted out around the 1900s, but you can see that geologists were not late. The Milky Way dimensions were only sorted out in the 1920s. And by that time, we had already figured out most of the Earth structure. The Spring-Russell diagram for star evolution came just as we were unraveling the Earth's internal structure. The expansion of the universe was developed in the 1930s and later. And again, it was just as we were sorting out the history of the Earth. And the first galactic models came just about the same time as the plate tectonics revolutions. You can see we were just almost synchronized with the study of the universe at large. And just to give you a small perspective from the thermal evolution side, energetics have always been a key consideration. They were certainly a key consideration, for example, in model of star evolution, but they've always been important for the Earth. And there were, of course, the very first attempts to study the Earth as a global system on a large scale. Now, the assumptions that were made for a long, long time were that heat transport was achieved by conduction in a motionless system. There were key problems with the initial conditions. There was a big debate about that. The observed heat flow was, of course, used, But we had to wait until Teddy Bullard to launch a series of systematic heat flow measurements both on land and at sea before the pictures started to become clear. And then radiogenic production came also. And just to give you an idea of what, in 1964, just before really plate tectonics started to emerge, there were models that were considered, for example, by McDonald in 1964. What you see here is a plot of temperature, that's the abscissa, as a function of depth in kilometers. The dashed lines indicate the solidus and liquidus of material that was supposed to be basalt, essentially. And you have two curves that were calculated on the basis of transient cooling models with two different values for uranium contents. And the uranium contents led to thorium and other radioactive compounds. And so basically, this was the status of the knowledge in those days. You can see that the curve with uranium is 5.5, etc. in units, starts to intersect the solidus, and this was not considered acceptable. In those days, it was already known that this uranium content was a bit lower than were the true values. So this was considered a big stumbling block and a big something that was not correct. So then the arguments that were made in those papers in people's studies were, is conductivity transport, is it correct? Initial conditions, what do we understand? Observed heat flow, is it correct? And there were a lot of scatter in the heat flow measurements. And what about our estimates of radiogenic heat production? And of course, to avoid the melting in the mantle, the solutions that were mostly discussed were initial conditions. There were some early models with the Earth as a cold planet, thermal conductivity at depth, conservation of heat-producing elements. If you concentrate all these elements in a surface layer, then you get rid of most of the problems. But this was considered not acceptable and not consistent with what we knew. And convective motions were mentioned as a potential solution to the problem. I think it's interesting that the energetic problem was not considered. Convective motions was obviously a key solution, but could not be advocated on the basis of what we knew then about temperatures and mechanism of heat transport. So it had to come from observations on other side, from geology and from the structure of the seafloor, that convective motions, which solve the problem of the Earth's circular evolution, that's where the evidence came from. I'd like to finish by the fact that we are dealing with rocks, and rocks are not easily studied. You have to dig them out of the ground. And when I was a graduate student in the early 70s at the School of Mines, a very distinguished geology professor told us, you may have heard about plate tectonics. This is very probably true, but it serves no purpose. So I will leave you with that statement.